Hey everyone. All right. So today we're kind of tying two ideas together. So it's all the motion stuff, but now rather than me giving you a position function, I'm going to give you a derivative graph, or I'm going to give you the velocity graph. So we've actually done this before when I give you derivative graphs and ask where the original function's increasing, decreasing, where the original function's concave up, concave down. It's exactly that lesson again, but now just looking at it in terms of this is a velocity curve. So it's pretty much what we've done. So this should go pretty quickly. So just remember that this is the velocity curve. And I'm going to ask you questions about the motion of this particle. So we have this curve. This is not the position curve, okay? So in the last discussion, I was telling you to do things with position, and you'd be like, oh yeah, okay, this particle had a negative velocity, so nope, it's none of that. We have to actually look at this like it's the derivative. So there's a couple ways to do it. You can go back to the curve sketch approach. I'm gonna kind of just think of this as, when we're above the x-axis, that means the velocity is positive. That means the original particle is moving forward, all that stuff. So let's see if we can kind of put this together. Here's how I like to do it. I like to identify the roots first. I think looking for the roots of the derivative graph, that's really what this is. Because remember, velocity is the derivative of position, is a helpful thing to take a look at. So I have critical points at x equals 1, 4, and 7. And I know you're like, well, those are roots. Yeah, they're roots of the derivative. So roots of f prime. So they're really critical points in the original function. Well, in motion problems, this is where the particle is at rest. So a lot of times we may just ask, where's the particle at rest? Bam, those are the spots. So let's start talking about where is the particle moving forward. So we'll say this is all forward, backwards. So remember, forward, right, up are all the same. That's positive. Backwards, left, down is all negative. So let's talk about where's the particle moving forward. Well, when the particle is moving forward, that's when the velocity is positive. And where the velocity is positive, if this is the velocity graph, that's where the graph of velocity is above the x-axis. So looks like this section we're positive and this whole section we're positive. So velocity is positive, meaning we're moving forward from time 0. We can actually use the bracket here because we're starting at time 0. And at time 0, I have initial velocity. The velocity at time 0 is somewhere up here. So it's kind of like v of 0 is approximately 5. So we have initial velocity. We're actually moving when time starts. Up to our critical point, which is at 1. And then the only other time we're moving forward is from 4 to 7. Okay, so then when are we moving backward? We're moving backward when velocity is negative, which means the graph of velocity is below the x-axis. So we're kind of implying all of our curve sketching stuff, or we're utilizing all that curve sketching stuff. So that would be this interval and this interval. So it looks like from 1 to 4, the particle is moving backwards, and from 7 to infinity, or whenever my interval stops. Because remember, this is the velocity graph. Velocity positive, I'm moving forward. Velocity negative, I'm moving backwards. Okay, so those are some of the things I can ask. Other things, in this case, I can ask, when is the particle speeding up or slowing down? So let's talk about speeding up. Speeding up means velocity and acceleration have the same sign, meaning they're both positive or they're both negative. Well, where is that happening? That would be where velocity is above the x-axis and acceleration, which is the derivative of velocity. So we'll write the derivative of velocity, which is acceleration, is increasing. Well, I guess I should say that's positive. So let me put it this way. So it's where the velocity is increasing. Because remember, if velocity is increasing, that means the derivative of velocity is positive. Derivative just means slope. So if my slope is going up, my slope is positive, that means I'm increasing. So you need to find on this where is velocity above the x-axis and increasing, or where is velocity below the x-axis and decreasing. And that would be slowing up in the reverse direction. So let's see if we can figure this out. First, velocity above the x-axis. Well, you already have those two spots. And it's increasing. Well, it's not doing that in the first part, but from this piece to this piece right here, this section right here, we have velocity increasing and it's positive. So from 4 to about, what is that, 5.7-ish. So on the interval from 4 to about 5.7-ish. So where is velocity below the x-axis and decreasing? Well, let's see. It looks like right here, this interval right here, and for the rest of time here. So that's decreasing, and this is decreasing and below. So that looks like from 1 to about 2.2 and 7 to infinity. So zooming out just a little bit, this is speeding up in the forward direction. And this one is speeding up in the backwards direction. Okay, and that's kind of a complete analysis of motion for now, based on a velocity curve that we can do. Now in the discussion, I ask you a really important question about what you think is going on in terms of, if I have a velocity curve, can I find anything about position? Right now, as we are in the class right now, we don't know anything about position if I have a velocity curve. So if I start you out with a velocity curve and I ask you something about where are you located or total distance or displacement, we can't do it. We don't know yet. I'm telling you right now, a big theme of second semester, we are going to be able to answer that question. And I'm not going to give it away right now. So if you're starting to feel what's going to happen, I think I've talked to a couple of you guys about it, but think about how I can use a velocity curve to talk about total distance or displacement. There's a way to do it. It's the big theme of second semester. I'm not going to give it away. All right, so there's our first example. Let's talk overall about what happened. So according to everything I said here, particle started by moving forward. I don't know how much. I just know it moved forward. It stopped. Oh, we forgot slowing down. Oops, sorry. Let's do slowing down real quick. Slowing down. Dang, I thought it was done. Slowing down is when velocity and acceleration have opposite signs. So that would be when velocity is positive or above and acceleration is negative, which means velocity is decreasing because acceleration is the slope of velocity. Where is that happening? So where am I above and decreasing? Looks like right here and right here. So the interval from 0 to 1 and the interval from that point up there, 5.7-ish to 7. I'm actually going to go back and bold this a little part. So it looks like we only have one little segment left. We already talked about this. We were speeding up right here in the forward direction. Okay, last piece. Where am I slowing down? Where they have opposite signs. So the other case would be, let's do this one in purple, where velocity is negative, so below, and acceleration is positive, meaning velocity is increasing. And that happens at the interval right here, this last piece. So you should have every interval accounted for. That looks like my, what is it, 2.2 to 4 interval? 2.2 to 4. Cool. Okay. So now let's talk about the motion of this entire particle. Hopefully you guys can see that. We'll deal with this one somewhere else. Okay. Come on. All right. So what happens? Mr. Particle starts out moving forward. He has positive velocity. I don't know where he's located. I just know he's got positive velocity, but he's slowing down, stops, speeds up in the reverse direction because he's got negative velocity, and velocity is decreasing, which means acceleration is negative. He, at time 2.2-ish, doesn't stop. He's still moving backwards because velocity is still negative. So remember, this is a velocity curve. Velocity is still negative. He's still moving backwards, but he's slowing down. And then at time 4, he stops and begins going forward and speeds up. So begins going forward and speeds up. And then at time 5.7-ish, that's when he begins slowing down. He's not stopped there. He's slowing down in the positive direction. And then at this root at 7, that's when he begins moving backwards again. And that's when he begins speeding up in the reverse direction. Okay. You can do that. That's a good combination of motion and curve sketching. And this is what most of the FRQs are on in the traditional AP test environment. They start you with a velocity curve or derivative curve and ask all this stuff, plus a major component that we're going to get to second semester. So if you're wrapping your mind around this, that's good. Let's do one more. Okay. Let's do one more. So here's my other one. See if we can do all the same stuff. So can we talk about where's the particle stopped? So when is the particle at rest? So again, this is a velocity curve. Let's see if we can identify moving forward, moving backward, and then let's see if we can talk about speeding up, and let's see if we can talk about slowing down. If you feel like you have a handle on it, I would try doing this ahead of me. That way, you can check yourself and see if you're right. Okay, so we have our velocity curve. So first things first, when is the particle at rest? At our critical points. Here, here, here. So it looks like a t equals 1, t equals 3, and t equals 5.5. That's when the particle stopped. Now, when is it moving forward? When velocity is positive. So in this case, this is the velocity curve, so above the x-axis. Okay, don't get confused. This is not a position curve. Position would be totally different because then it would have a negative velocity to start. So look, we have positive velocity to start. Because my derivative is positive, the particle is moving forward. If I looked at this like it was position, the particle would be moving backwards. It's not position, it's the velocity curve. Okay, so I'm moving forward in that section and I'm moving forward in this section. So that looks like the interval from 0, again, I had initial velocity in this case, to 1, and then from 5.5 to infinity, or the end of the interval or whatever. Moving backwards means when I'm below the x-axis, so here and here. Now, yes, I stayed under the entire time. However, you should still break it up because at time 3, I'm at 0. So you should say I'm moving backward when velocity is negative, which means below the x-axis. And that is from the interval from 1 to 3 and 3 to 5.5. Speeding up. Speeding up means they have the same sign. So where velocity is positive and acceleration positive. Let's do that one first. So velocity is positive, and acceleration is positive. It looks like this strip right here. Looks like that piece right there. That's the only time where they're both a positive and increasing. So that interval looks like 5.5 to infinity. What about when velocity is negative and acceleration is negative? That looks like this little stretch right here and this tiny little stretch right here. So let's say the first one's like 1 to 1.5 or so. and 3 to, let's say, 4.5. Again, I'm not too picky about if this is 5. Yeah, 4.75. Sure, why not? As long as you're between 4 and 5, I really don't care. Yeah, I'm not. The graphs, it's hard to get them all perfect, so it's fine. Don't worry about it. All right, slowing down. When velocity is positive and acceleration is negative, where does that happen? Velocity is positive, acceleration negative here. Wow. Let's try to stay in the lines a little better. This piece right here. Beautiful. That's 0 to 1. Any other spots? No. How about when velocity is negative and acceleration is positive? So that would probably be this last little piece right here. So 1.5 to 3. And this little piece right here, 4.75 to 5.5. All right, so what did Mr. Particle do here? Something kind of unique that I want you to pay attention to. He started out going forwards because velocity was positive, but slowing down. He stopped at time 1, then began going backwards, speeding up, began slowing down at time 1.5. Still moving backwards, slowing down, came to a stop here, but something interesting happened at this part right here. He didn't change direction. He stopped, and then he kept going backwards. It's an important thing to pay attention to. So I went backwards, stopped, and then continued moving backwards, speeding up in the negative direction. And then I slowed down in the negative direction around 4.75, stopped at 5.5, and then sped up and yipped on to infinity. Okay, so a little bit trickier when we're dealing with a velocity curve. So sometimes I'll ask you, did the particle ever change directions or not? At these 2 points, I did change direction. But at time 3, he didn't change direction. He stopped and then continued going backwards because velocity stayed negative. It's only when you have a switch. And then remember, the critical points are where the particle changed from speeding up to slowing down. So it's a change in concavity in the original function. Is the curve sketching way we talked about it. All right, so that's basically it. Now, one other thing I'm going to start to do. That's the end of the lesson. So that's all I'm going to say on what the homework's about. But second semester is fast approaching, which means the AP test. Uh-oh, I froze. Wow. What a perfect time to freeze. Give it a sec. The AP test is fast approaching. And I want to give you opportunities to begin seeing some AP level problems. So I think what I'm going to do on every one of these at the end is include an AP problem on the topic if I can find it. And as we go farther and further along, I'll just include good AP problems that I think are worth trying. So here's where we're going to diverge a little bit. We've gotten to a point now where some of you are clearly doing well and you know you're going to take the AP test and you're probably going to do fine, so you need practice. There are others of you that are hanging on, but this is getting pretty grim. Happens every year. This is not a requirement of the class. I mean, we're going to be doing free response the second semester for sure, but I'm not going to ask you to show me this. This is more for you, okay? So if you're not, this is not your cup of tea, I'm not going to know. But I'm trying to include things for those of you that do want to take the AP test to give you a chance to see some of these, okay? So I like these problems. Why do I like AP problems? Because they're a little bit more of a challenge. So as a teacher, it's hard to differentiate between hitting all the major topics and keeping it in a way you can understand it and pushing you to do harder type problems that may be tricky. That's why I kind of like this idea of, look, for some of you that are willing to push yourselves and try to work beyond just the basics, this is a perfect time to do that. And definitely a lot of you are in that position. It's good to challenge yourselves, even though you're like, I'm never going to use this. That's not really the point. I learn a lot of things and do a lot of things I never are going to use in life. There's only a handful of things you're actually going to use in life daily: eating and sleeping and basics. This is a little beyond that. This is to make you a little more of a thinker, intellectual, challenge yourself, go beyond just what's required type of things. I'm all about that, if you know me. So if we were in class together a little bit more, I would have opportunities to talk to you more about how I feel about that. But I don't like it when people are like, when am I ever going to use this? Because you're right. If you're just stocking shelves at Costco and that's your job, fine. I mean, nothing wrong with that. But if that's all you know, you're a very boring person. Go beyond what your job is about. It's worth doing other things. I mean, some people like writing poetry. Is that useful? No, but maybe for you it is. I like reading about math. I like working on difficult math problems. It stimulates me in a way that I think is valuable. So I'm sure you guys are still young. You haven't really discovered what's, gives you joy. But finding things, challenging yourself, pushing yourself, doing interesting things makes you a more interesting person, and then you have more things to share with other people. That's what I feel. So again, I like these challenging problems. Let's get to it, but I won't give such an intro the next time. I think these are worth doing, especially if you plan on taking the AP test and want to save tons of money. So here we go. You have a position function, x of t equals, one of my favorites. Look, they keep things general, t minus a and t minus b, where a and b are constants. A and b are constants, and a is not equal to b. They want to know for what value, which of the following values of t is the particle at rest? When is t, or what values of t is the particle at rest? When is particle at rest? Okay, and this is a multiple choice, so they give some answers. They give some options. They say t equals a plus b over 2. T equals ab. T equals a plus b. T equals 2 times a plus b. And t equals a and t equals b. Okay. Now, sorry, covered up a little bit. This is a good testing problem because here's the deal. Sometimes people are like, this problem's too hard. If I can go through it and do it all with math you understand, it's not too hard. It's a challenging problem, but it's not unfair. Now, if I gave you a problem that looked like this and asked you if it converged or diverged, that's unfair because that involves a symbol you've never seen. I use two phrases, converge, diverge, you've never seen. That's unfair. But in a problem like this, where oh, I know what a position function is. I know what it's asking particle at rest. I know how to do that. That's not an unfair question. That's just a challenging problem. But there's a difference. I always get annoyed when kids are like, no, it's too hard. You never taught us this. Yes, I did. I taught you every single component I'm about to show you. It's just asked in a weird way. So you should try it ahead of me. If you're really on with what I'm putting down, you should try it on your own. But I'm going to show you how I would go about this. It's asking about particle at rest. That means I need a derivative. I need to find the velocity. So the velocity, as we know, is the derivative of position. I'm going to do product rule. So there's your first function. There's your second function. Derivative of the first. A is just a number. So the derivative of a number is 0. So the derivative of this first one is just 1 times the second. So times t minus b plus derivative of the second, which is 1 times original first. Set that equal to 0. Set the velocity equal to 0. And let's solve for time. So 0 is equal to 2t minus a minus b. I'll add the a and the b over to the other side. And I'll divide by 2. So t equals a plus b over 2. That's the time that would cause the velocity to be 0 for whatever values of a and b are. And we don't know what they are. That's it. Okay, not a hard problem, but looks tricky. And typically that discourages people from trying it. But not a hard problem, I don't think. So I'm going to continue to do some of these, sometimes a little bit harder than others. But I think you should try them, especially if you're going to take the AP test, because if we can do enough of these between now and then, the AP test will feel like a breeze. Plus, I'll try to do some review in these ones too. So, all right, that's it. Thanks for sticking with me. Do the homework.